Thank you. Thank you very much, Shirshendu. And so let us go ahead with the considerations that were done yesterday. Let me recall very quickly that in order to introduce this concept of randomized observability constant, we used this very, very beautiful trick that was introduced to me by Nicolas Burck, and that consists of randomizing the initial conditions of the wave equation by multiplying each of the coefficients aj and bj standing for the initial conditions by some random laws, like typically Bernoulli, plus or minus 1 with probability 1/2. And so this trick, as I said yesterday, is coming from old works by Palais and Zygmunt 1 century ago. They used that in order to prove that actually almost surely you take any Fourier series in L2, and actually almost surely it is in any space LP, which is impressive. And for the little story, Burck and Zvetkov so rediscovered that very beautiful trick, made it popular in the... Sorry. I do it like that, maybe. Yeah. Made it popular some 15 years ago. And actually they used that trick at the beginning for nonlinear waves, nonlinear blowing up waves, in order to prove that essentially, almost surely, nonlinear waves that are known to blow up actually do not blow up. This is interesting. And the trick was used to, some 5 years ago, something like that, maybe a bit more, also to prove the same kind of things for Navier-Stokes equation. Generically, in some sense, in some probabilistic sense, if you choose by chance initial conditions, then you have no blow up. It's very a powerful trick. And so here, as I showed yesterday, I only used that trick in a very basic way, because what do Nicolas Burck and Nikolai Tsetkov is much finer, actually, and much more difficult. Here, I only use the trick in order to kill all terms outside of the diagonal in a quadratic form. That's all. That's all I do. So this is the computation I showed yesterday, and that allows to show that the randomized observability constant that we introduced, which is the randomized version of the observability inequality, has a nicer expression, which is that guy. So do not care now about the time capital T, because you see the time capital T will be a multiplying scalar. So in what follows, it won't play any role. And you have an infimum of spectral quantities with a coefficient here in front of the integral. This coefficient is exactly equal to 1 whenever you deal with wave or Schrödinger equations. And when you deal with parabolic equations like the heat equations or the Stokes equation, it is some exponential, right? It's an exponential of the eigenvalue. Right? So, but again, that trick can also be seen for the Gramian. If you look at things a bit more abstractly, I already explained that the deterministic observability constant is nothing else but the lowest eigenvalue of the Gramian operator. So the Gramian operator, you can see it as an infinite matrix, which is full, right? It is symmetric, and the deterministic observability constant is the lowest eigenvalue of it. Now, if we use the trick by Nicolas Burck, by Palais Zygmunt, the Gramian is seen as a bilinear form, right? And you kill all terms outside of the diagonal thanks to the probabilistic trick, right? So finally, the randomized observability constant is now just the infimum of the diagonal elements of the Gramian. We can redo if you want. We can redo the complete computation, but this is just what I said. The deterministic observability constant is the lowest eigenvalue of the Gramian. And the randomized observability constant is the infimum of the expectation of this scalar product, which kills all terms off diagonal, exactly here. Exactly the same computation I did yesterday. You see, you expand the quadratic form here, and all terms that are off diagonal, so when J is different from K, are killed by the random laws, by taking the expectation. Right, so this is the trick. Of course, you always have an inequality between the deterministic observability constant and the randomized observability constant. I mean, the randomized observability constant is always greater than or equal to the deterministic observability constant. Logically, I mean, the deterministic observability constant is an infimum over all initial data. So it is a wider set, while the randomized observability constant is an infimum over almost all initial data. So obviously you have an inequality. And we will see in what follows, this was more or less one of the questions by Shirshendu yesterday, we will see that actually this inequality may be strict. Actually, it is strict most of the time. Oh, for any time.
For any time, large time also this is?
Yes. You are right. We saw in the first part of the lectures, we saw the role of the time in the value of the deterministic observability constant. For GCC, Ct of omega is equal to 0 when t is too small, but it may become positive only if t is large enough because of the GCC. You are right. It is not the case for the randomized observability constant because t plays no role in the randomized observability constant. The randomization killed completely the geometric considerations. This is a way to say it. I said also yesterday that, but it's only a conjecture, I showed you, the deterministic observability constant should be the minimum of two quantities. One is purely spectral, one is purely geometric. The spectral quantity is exactly that one. And the geometric quantity is the GCC functional, LT, you remember. And so in some sense, randomization has killed the geometric part. Okay, so as a conclusion, so you see, we had a long discussion on how to model the optimal observability problem. And here, the conclusion of this discussion is that we choose to model the problem as this one. That is the problem of maximizing over the set of all subsets small omega that have a fixed Lebesgue measure, this spectral functional, which is the infimum over all modes of some coefficients, times the energy of the jth eigenfunction restricted to the subset omega. Okay, for those of you who are acquainted with quantum mechanics, maybe, probably you know what is this quantity, right? Well, if you take an electron It is the probability for an electron to be on a certain level at some precise position. It has an interpretation. For us, as we saw it yesterday from a point of view of mathematician, phi j squared dx is a probability measure. And so this is, if I call it mu j, this guy is mu j of omega. Okay, this I will switch. This is in my slides if you are interested. This is other ways to arrive at the same criterion, but I will just switch that. Okay. But definitely, so let us investigate this problem, which corresponds to maximizing the randomized observability constant. Of course, I do not say that maximizing the deterministic observability constant has no interest. I'm not saying that. It has an interest, but I still do not know how to solve the problem. It's more difficult. But I also showed yesterday that in practice, what is interesting to engineer is really to maximize this randomized observability constant. Oh, and I forgot to say too, that the Palais-Zygmunt procedure, Burke procedure, consisting of randomizing initial condition, creates indeed sets of initial data that have full Lebesgue measure in the set of all initial data. This is important. So we really deal with almost all initial data in a strong sense. Right, so let us attack the solving of this problem. And just before attacking it, I would like maybe to stress very, very quickly that this problem that we have modeled should be, of course, obviously independent of initial data. I just mean, in many, many papers, you can also see the problem of solving solving optimal observability for fixed initial data, right? Of course, this is mathematically interesting, but in practice, it has absolutely no interest. No interest, because imagine that you would like to design the best possible place and shape of sensors. Right? It should not depend, of course, on the initial data. Right? It is stupid. All the more that you do not know the initial data that you will reconstruct. Right? So obviously, the best shape and placement of sensors that you would like to design has to be independent on the initial data. This is why we took a supremum of an infimum. But if you suppress the infimum, then the problem is much simpler because it becomes a quite easy problem of shape optimization consisting for some fixed initial data of maximizing the corresponding energy, right? Again, you have only one solution of the wave equation. And you maximize this quantity over the set of all subsets. Well, so in that case, it is just a matter of applying the bathtub principle to find a solution. It is not an issue. Okay. So here, the problem that we consider should be absolutely independent of initial data. Another remark, as I said, the main problem that we will have to deal with, one of the main problems, is that we have no compactness in the set of unknowns. Instead, if you would have some, let's say, reasonable assumptions on the subset small omega, such as it should have finite perimeter, or maybe a finite total variation, or maybe enjoy some regularity properties, or maybe it should range over some finite dimensional subspace. I mean, you have only a finite number of parameters on which you can act. In all such cases, you would get a compact set of possible unknowns, right? And in that case, you would immediately obtain existence of an optimal set. But in our works with Priva and Zoisois, we wanted absolutely to avoid to put any such assumption. And I will show, by the way, in the rest of the talk, that if you put such assumption, okay, you get an existence of an optimal set. But maybe then if you let the bound capital A here, for instance, tend to the infinity, then probably you will see the complexity of the set that increases. Right. So, and still before solving, also I have stressed, but I will pass this part, that there are many other related problems to that problem of optimal observability, such as the problem of optimal controllability. You can ask exactly the same question whenever you want to control a wave equation. What is the best set on which you can act? It's the dual problem. You could also ask the question, what is the best set in order to stabilize the wave equation? I mean, we saw with Arrow theorem that for this wave equation with a localized damping, as soon as omega satisfies GCC, you have observability then of the conservative wave equation, and thus by Arrow theorem, you have exponential stability for this damped wave equation, right? So now, question, what is the best possible subset omega having a fixed Lebesgue measure for which the exponential decay is the best possible? I show actually in the following slides that this is the same problem. This is the same problem. So you can read the proof if you want, but I will just go ahead. Okay, so let us solve the problem. Let us attack it. Here is the shape optimization problem we want to solve. And as I said at the beginning, the solving will be very different according to whether you consider parabolic equations or hyperbolic equations. This will be very dramatically different. In the parabolic equations, moreover, you have coefficients in front of the integral that are exponential. Right? While for wave and Schrödinger equations, this coefficient is equal to 1. And as I already said a bit yesterday, quite clearly, you will have, in order to solve this problem, you will have to understand what happens for high frequency modes. Because here, we take an infimum over all modes, all integers. So clearly, we should get some knowledge of what happens whenever j tends to the infinity. It will be required. So we have to get some knowledge on the asymptotic behavior of the squares of the eigenfunction. And obviously, there should be then a strong difference between parabolic and hyperbolic equations, also because of the value of the coefficients, quite clearly. And this is what we are going to see. So, first problem, which is difficult. You take this shape optimization problem, and you wonder whether there exists an optimal set. As I said, it is difficult because we do not have any good compactness properties. The set of unknowns is the set of all possible measurable subsets, small omega, that have a fixed Lebesgue measure, that is this is what I denote by capital U sub L, right? This is the set of unknowns. Okay? And the set of all omega, or characteristic function of omega, it's the same, with values in 0 or 1, such that their integral over the whole capital omega is equal to some fixed real number. So this set of unknowns, UL, has no good compactness properties. Really not. So probably a first thing that we can do is to close it. It is even not closed, right? But let us close it. It is called, in shape optimization, this closure procedure has a name. They call it a relaxation procedure. So let us relax the problem. So we do consider the convex closure of UL for the weak star topology of L infinity. Then it is this set of all functions A on capital omega that are measurable and that take their values between 0 and 1, such that their integral over the whole capital omega is equal to the fixed Lebesgue measure. This is the convex closure. I mean, instead of having, if you are on 0, 1, if you take characteristic function, so this is something like that, instead of that, you relax this set to the set of all functions A, not necessarily continuous, of course, but taking all possible values between 0 and 1. And so what we call the convexified or relaxed problem is now this problem where we replace omega, or the characteristic function of omega, by a function A of x. Exactly as we did before, you remember, with the observability constant. Exactly. Except that now, UL bar is compact, weakly compact. That's nice. This is a good hope to get an optimizer. Moreover, you can notice that, so UL bar is convex and compact, and its extreme points are exactly the characteristic functions. So if you imagine a convex set with extreme points, the extreme points are exactly the characteristic function, that is the point, the elements of UL. So, it is not difficult, of course, now to see that this relaxed problem has at least one solution, that is denoted by A star. How do you prove that? It's very easy now, because for each j, the functional gamma j times the integral of A phi j squared is, of course, linear and continuous. Now, what you do, you take the infimum of them. So, you take, like that. You take an infimum of linear functionals. Of course, what you get is a concave functional, which is, moreover, upper semi-continuous. Okay? Classical result. So, the functional capital J that is here, that is defined as the infimum, is concave, upper semi-continuous, and UL bar is compact, so you have a maximizer. Okay? Of course, so now that you have the existence of this A star, of course, now what you would like is to come back to the initial problem and try to ensure that such a maximizer is indeed the characteristic function of some subset. This is now the game. We would like to prove that this maximizer is actually an extreme point of UL bar, which is not at all obvious. We are not in finite dimension, right? In finite dimension, okay, it would be the end of the game, because we would be automatically at the boundary at an extreme point. But no, not here. We are in infinite dimension. Does not work. And as we are going to see, mainly, to spoil a bit, like Shirshendu likes to do, I will give a positive answer, positive and very satisfactory, I would say, answer in the parabolic case, but non-satisfactory and rather negative result for wave equations. Let us go ahead. First of all, in order to maybe to gain some intuition on the problem, and also in order to approach it from the construction point of view and numerical point of view, a natural idea is also to truncate the problem, because we see that there is a problem certainly with high modes, high frequency modes. So let us truncate. It's natural. Let us truncate the infimum over all modes to an infimum, or minimum now, over capital N modes, like that. It's very natural too. And of course, we would like to hope a gamma convergence of this truncated Pn, problem Pn to the initial problem P. We would like that. Again, we will see that there is such a result in the parabolic setting, but certainly not for waves. Now, anyway, this problem is very obvious. For this problem, we have, so it's a shape optimization problem, but with a finite number of functionals. And we are going to see that this problem has a unique solution, which is, let's say, a subset that I will denote by omega n, to underline the dependence on n. And moreover, this subset is very nice, very nice. It is semi-analytic. It means that it has boundaries, and the boundaries are made of analytic functions. Very, very regular. It has a finite number of connected components, and all we want. To prove this result, it's very elementary. You look at, again, the functional here, the minimum over all modes, over capital N modes, it is Jn, right? Exactly as before, Jn is concave, upper semi-continuous. It has at least one maximizer. Let us denote it by An. Now let us prove that actually An is the characteristic function of some subset, omega n. So what we do is rewrite this finite minimum, this minimum over n modes. We rewrite it in a slightly more complicated way. We rewrite it as a minimum over all convex combinations of those integrals, right? What I use here is the minimum for j between between 1 and n of some quantities, I don't know, capital A, j, is equal to the minimum of the convex combinations. What did I use? Beta or something? Yeah, beta. Beta j, aj, over all beta j non-negative, n of sum equal to 1. Okay? Very useful formula. So this is what we write here. So now, the max-min problem above is written as a classical minimax problem, or maximin problem. It's the maximum over a compact convex set of A, of a minimum over beta, which is in the simplex, of a functional capital F, which is there. So capital F is concave with respect to A, convex, even more than that, but in particular convex with respect to beta. UL bar is compact. Sn, the simplex, is compact. So you can just use the classical minimax theorem, which is due to Sion, Maurice Sion, which says that you can switch max and min. What you cannot do in infinite dimension, right? Be careful. If we could do, again, the problem would be obvious. So you just switch max and min. Now you've got the minimum over beta of the maximum over all functions A of this integral. And moreover, you have the saddle point property, which is the classical property of the minimax theorem. But now, what I say is that this maximization problem can be easily solved, right? Because inside, probably it's on my next slide. Yeah, it's there. It's there. So look at just the problem of maximizing over A, the integral of A against some function, which is a phi n. Right, so you get immediately, again, it's a matter of bathtub principle, that an must be the characteristic function of some subset, which is just some upper level set of the function phi n. Right? That's all. Again, let me show you the bathtub principle in 1D. So let's say that you have a function phi n, which is, I don't know, that. And you want, so this is phi n. And you want to maximize integral of A phi n over all possible functions A whose values range between 0 and 1. So quite clearly, and with integral of A, which is equal to something, L omega. So quite clearly, you have to take a threshold somewhere here. I don't know. You have a threshold, which I denoted by lambda n. And quite clearly on the drawing, but it's very easy to prove, you have to take A equal to the characteristic function of omega n with omega n that is there. This is the way to maximize this integral, right? This obvious observation has a name. This is bathtub principle. I already told it, I think. The only case where the bathtub principle would not lead to a characteristic function is whenever the function phi is maybe piecewise constant somewhere, like that. And maybe if we are not lucky, maybe the threshold lambda n will be exactly at this level. Imagine. In that case, there is no uniqueness, right? In that case, there is no uniqueness. There are an infinite number of solutions. And actually, the solution is not necessarily an optimal set. We speak of a relaxation phenomenon in that case. So in the bathtub principle, the bad situation is when the function inside of the integral may be piecewise constant somewhere. So is it the case here? No. No, because the function phi n is a linear combination of squares of eigenfunctions. So under reasonable assumptions on the operator, the eigenfunctions are analytic, right? So the function phi n is analytic, and this never happens. Okay? Of course, for the wave equations, for the heat equations, there is no problem. The eigenfunctions are analytic. So we are done. We are done, and moreover, what I said is that omega n is an upper level set of an analytic function, you see? So it's a semi-analytic set. It is very, very regular. It's nice. So for this truncated problem, really no issue. There is one unique solution with a very, very regular set. But of course, it does not solve anything, because then the question becomes, okay, but does this sequence of optimal sets, omega n, converge to something? It's very, very not clear. So let us go first to positive result in the parabolic case. In the parabolic case, it is really fantastic, because in that case, we have a very definitive and nice answer. So here, by parabolic case, I mean you take your PDE, which may be the heat equation, right, in the form of dty equal ay, where A is an operator. It can be the Laplace operator for the heat equation. It can be the Stokes operator, or it can be also, interestingly, some real power of the Laplace operator. Fractional heat equation, something like that, which is called anomalous diffusion in the literature. Right, so in that case, we have the good convergence. And definitely we prove in this paper with Priva and Zoisois that there exists a unique optimal domain omega star. Moreover, so it's not the end of the theorem. The theorem has a sequel in the next slide. Moreover, this set, this best set, omega star, is semi-analytic. It's very regular. It's a good set. It's noticeable that for this optimal set, we can prove that systematically, it's always true that the observability constant estimated on this omega star is always strictly lower, unfortunately, I would say, than the randomized observability constant. It's always like that. I'm going to try to show what is difficult in this theorem, and the very key part of the proof is, you see, we were fortunate because we used a result that was just published by those guys, Aprez, Escoriaza, Wang, and Zhang. And it's really instrumental in the proof that we use exponential estimates on the eigenfunctions, which are very fine. This is an extremely fine result by those guys. Aprez, Escoriaza, Wang is Gengsheng Wang, who is now in Tianjin, and Zhang, because there are thousands, millions. Sorry? Sorry? No, there is no power 2 in the result, but of course by Cauchy-Schwarz you can now get the same kind of inequality with a square. But they gave it like that. They wanted to get some much finer Lebot-Robiano estimates in L1. Oh, this is a fantastic paper, really. And so Zhang, this Zhang is Zhan Zhang, who is in Wuhan. Was also my postdoc at some time. And so thanks to this guy, I will show why this result is very instrumental. And what is very difficult in their result here is that this result is uniform with respect to all possible measurable subsets omega that have a fixed Lebesgue measure. We were lucky there. We were lucky because without this result, we would not have proved anything. So it was just in time. Okay, and I give the reason here. Sorry. So just look at the bottom of my slide. So as I said, in the criterion that we have to deal with, mainly we have to look at what happens for high frequencies, right? This is the difficult part. So now let us look at high frequencies. So let us look at what happens when J tends to the infinity. So in front of the integral, we have an exponential coefficient. This is the gamma J. And then we have to deal with the integral of A against phi J squared. But now, thanks to the result of the four guys, this integral can be bounded below by some constant time a decreasing exponential. Right? This is according to their result. And here, we use in a very crucial way the uniformity with respect to the subset. If we don't have the uniformity, we are dead. Right? It's a very strong result. And once you are there, you see that here you have an exponentially decreasing coefficient, say exponential minus square root of some mu j, but which is against an exponential mu j to some power. So you see that if the power is appropriate, if the alpha there is greater than 1/2, you have coercivity. I mean, this criterion is tending to plus infinity at infinity uniformly. And so you are back to finite dimension. Right? This is the proof, more or less. So this is the main argument of the proof, which is finally not so difficult, but that uses a deep result. This result is deep and difficult. And so thanks to this kind of proof, you see that actually this unique optimal domain omega star actually coincides with the best domain omega n for some large enough capital N. That's all. So it's fantastic. It's the greatest result we could obtain. The previous sequence of optimal sets, omega n, I showed you, the solutions of the truncated problem. If you look at its evolution as function of n, actually it is a stationary sequence. It's fantastic. It's the best possible convergence. Omega n converges after a finitely many steps. It becomes stationary, and as soon as it is stationary, it means that you have reached the very best observation set, omega star, for the whole problem. End of the story. So for sure, for instance, what what was interesting to people doing shape optimization, who always care about the fact, okay, is my optimal set fractal or not? No, here it's not at all fractal. It's very nice. It is semi-analytic. Great. And moreover, this theorem even shows you that you can now design a very efficient numerical approximation procedure because you just have to solve the truncated problem. That's all. So let us solve it. This is the complete proof, but I switch it. You can read it if you want. It's not difficult. Let me show you. Before that, let me recall that this theorem can be typically applied to the heat equation, more generally to anomalous diffusions. I mean, with an alpha large enough, more than 1/2, which is for those who are acquainted with the control of such anomalous equation, which is the threshold of null exact controllability. Right? For any such alpha greater than 1/2, this equation is exactly null controllable. But for lower alpha, it is not. We do not use that fact, but it is noticeable. Or you can also apply it to the Stokes equation as an example. Okay, let me show you some numerical simulations. I promised I would show you the optimal thermometer, so here it is. So let us take as a domain capital omega, let's say the square. Okay? The square, right? Let us choose capital L equal to 0.2. It means that inside the square, you are allowed to spread 20% of the surface as being sensors. Right? This is what you are allowed to do. Now, as I said, let us solve the truncated problems. So we solve them with only one mode, and this is the optimal set, with only one mode. Now we increase step by step the number of modes. We take 4, 9, 16, 25, and so on. And you see that quite quickly, evidently, the solution becomes stationary. It means that this subset, omega star in green, is the optimal set. You have reached it. It is the solution of the whole problem. It is the solution maximizing the randomized observability constant. So this is what we can call the optimal thermometer, which is maybe not that appropriate. Okay. I agree. But that's it. I forgot to say, but this was for the heat equation with Dirichlet boundary condition. I forgot to say. If you would like to see what is the optimal thermometer for Neumann boundary condition, it is rather like that. Okay. Mainly you have to observe, you see, around the boundary. Now, interestingly, you can also solve completely the problem of optimal observability for any anomalous equation, anomalous diffusion. I mean, for any positive power of the Laplace operator. It can be done, but by hand, not with my previous theorem. Because in my previous theorem, I required that alpha was greater than 1/2. But now my claim is that we can solve actually the problem for specific domains capital omega for any alpha positive. So we can solve it in the square. It's an exercise with Fourier analysis. And we can solve it also in the disk. And then it is, not surprisingly, of course, we have to use Bessel functions because Bessel functions are used in order to parameterize eigenfunctions, right? But what is interesting is that for the case which is not covered by the previous theorem, alpha less than 1/2, then the optimal set is in that case an infinite number of concentric rings that accumulate at the boundary. So you see, it becomes much more complex. It has an infinite number of connected components. It is not semi-analytic anymore, not anymore. And even, also interestingly, and like for controllability, but I'm not able to explain why, if you take alpha equal exactly to half, then this can work only if capital T is small enough. Okay. But the proof of that is extremely technical, actually. It requires quite fine properties of Bessel functions. I can show you some numerical simulations. Here it is for the usual Laplacian. So, I mean, this is the optimal thermometer in the disk. Okay. Strange guy. Concentric rings, right? And this is here. If you take alpha less than 1/2, then you have an infinite number of concentric rings accumulating at the boundary. As I will explain in one moment, actually this accumulation at the boundary is not a surprise. And I will tell you why in one moment. It's because of quantum limits, again. I will tell you why in one moment. So this is the final point, let's say, to what I would like to say about parabolic equations. It's a kind of definitive result. We are happy with it. Now we are much less happy for hyperbolic equations, Wave and Schrödinger typically, where the coefficient gamma j is equal to 1. So now here what we have to solve is this problem. The maximum over all subsets omega of the infimum over all modes of the integral of phi j square restricted on omega. Now, at least what we are going to prove, I'm going to give more details in one moment, is that we are able to prove under strong spectral assumptions, and I will say unreasonable spectral assumptions, like that, we are able to compute the optimal value of this problem. We are able to prove that this supremum is equal to capital L, which is only a partial result. So how will we prove that? First, let us come back to the convexified problem. And for the convexified problem, the result is easy. So the convexified problem is the problem in which you replace chi omega, the characteristic function of omega, with a function A in UL bar. In that case, the supremum is a maximum. We already saw that. And so the claim is that this maximum is equal to capital L. And moreover, and it's easy to see, the maximum is reached not only, but for instance, with the function A star, which is constantly equal to capital L. That is the constant function, which is not at all a satisfactory function, right? Because it's far from being a characteristic function, and it is a kind of average, right? A kind of homogenization. You put a percentage of sensors everywhere in a uniform way. It's very not a good answer to engineers, right? But let us already prove that. So let us prove that this maximum is equal to L. It's coming again, the answer is coming again from microlocal analysis. So this is why I will give the proof. Okay. First, when you take A equal L, which is in the set of unknowns, right? Then, indeed, the functional J, oh sorry, I forgot to recall, but J of A is equal to the infimum over J of the integral of A phi j square. So when you take A, which is constant equal to capital L, then of course you put the L outside of the integral. The integral of the phi j square is just equal to 1. And so you obtain J of A equal L, which is equal to L. So it gives you the fact that the maximum of J is greater than L. Obviously. Now let us prove the converse inequality. And this is the converse inequality that is coming from microlocal analysis. So let us prove that the maximum of J is less than L. So let A star be a maximizer. What do we have? So J of A star is by definition the infimum over J of integral of A star phi j square. Let us use again the trick I was given here. So the infimum over all modes J of those integrals is also the infimum over a simplex. But be careful, it's now a simplex in infinite dimension, right? So you take an infinite linear combination of the integral of A star phi j square. So here the coefficients alpha j are all non-negative and their sum is equal to 1. Be careful, there is no minimax here because L1 is everything but compact, right? There is absolutely no compactness. So no hope to use any minimax. Forget about that. Now, the infimum over all alpha of this linear combination is in particular less than the infimum over all indices capital N of A star against this Cesaro mean, 1 over capital N, sum of phi j square over the n first modes. Why? This is because you make the particular choice of alpha j, you choose alpha 1 equal alpha 2 equal blah 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 equal alpha capital N equal to 1 over n, and all others equal to 0. It's a particular choice, and since I take the infimum, I have this inequality, right? So I'm integrating A star against the Cesaro mean of the squares of eigenfunctions. But now it's a known result. It was known by Ormander already in the 60s. This sequence of Cesaro means it's a function, right? But it's a function that converges to the constant, so 1 over volume of omega. You can say 1. You can take volume of omega equal to 1. So it converges to 1 uniformly on every compact subset of capital omega. Uniformly, I mean in C0 topology, which is more than enough. I will show this lemma, which is more than enough in order to infer that the integral of A star against the Cesaro mean converges to capital L as capital N tends to the infinity. And so we are done. Okay, and the proposition is proved. Now, let me prove the result on the sequence of Cesaro means, because this is the microlocal analysis part. So it's not difficult. It's not difficult, and again, it is the kind of result that can be much, much generalized. And this is why I give it. So the proof goes as follows. Actually, you use the local veil law. More precisely, you consider the heat kernel for the usual Laplace operator. So let me recall that the heat kernel is by definition the Schwarz kernel of the heat semi-group, right? Is the function that allows to give all solution to the heat equation. You integrate it against some function f along the diagonal. Then the local Veil law is that the result of this integral is something like a constant, which is a geometric constant. It is some volume, but I do not need that here. But divided by t to the power n divided by 2. Right? This is a well-known result, which is called the local Veil law. And this equivalent is valid when t tends to 0. So n here is the dimension of capital omega. But this result is actually fairly much more general. In general, you should replace the topological dimension here with the Hausdorff dimension. Here they coincide. And then, now you recall that the heat kernel, it should be called something like Metzler formula or something like that. The heat kernel is nothing else but also an infinite sum. It is given by the infinite sum of exponential in time times the phi j square, where the phi j are eigenfunctions. So what you do have is, finally, what you do have is that the sum over j of exponential minus lambda j t is equivalent as t tends to 0 to some constant divided by t to the power half of n, right? This is what you get. Oh, sorry, I forgot integral of f phi j square. Sorry. What I wrote was valid for f equal 1. And now you take the inverse Laplace transform of that. Formally. And if you take the inverse Laplace transform, you obtain exactly this equivalence. So you obtain that the sum of the coefficients over there, which are the integral over capital omega of the phi j square f, for the lowest modes, lambda j less than n, should be equivalent as lambda tends to the infinity to some constant times lambda to the power half of n. Now, formally, this is just an application of the Laplace transform, inverse Laplace. Inverse Fourier, if you prefer Fourier, right? Be careful, it is just formal because, well, you are near the dangerous set, you are near the asymptotics. So the fact is true, but it's a theorem. And this theorem is well known in the theory. It is called Karamata. It's a Tauberian theorem. It is called Karamata. Karamata theorem, which is proved, for instance, in the book by Feller or something like that. Right. It's a well-used tool in a microlocal analysis because it is always the way people derive Veil laws. So it's a basic result form. It's always that way that you can derive Veil laws. You derive an estimate on the heat kernel along the diagonal, then you apply Karamata and you obtain the Veil law. That's the Veil law, as you can see. If you take f equal 1, then you have exactly, this capital N of lambda, the Veil counting function. Right? It's exactly that. The number of eigenfunctions less than lambda, capital N of lambda. The Veil counting function. Yeah, look. Yeah. If you take f equal 1, you see, you are summing 1 over the lambda j less than n. So it is the number of eigenvalues less than n, which is usually denoted by capital N of lambda, the veil counting function. And so this result says that capital N of lambda is equivalent to some constant times power of lambda, which is the veil law. Right? So, sorry, Maity? Yeah? Lambda is going to infinity, yes. Yeah. Oui? Oh, it's not the same n. Oh, yeah. Okay. Oh, I missed. Sorry. This is lambda. I'm sorry. I'm sorry. Yeah, yeah. I'm very sorry for the misprint. Yes, yes, yes. Sorry. Yeah, because here capital N was something else. So I'm sorry for the confusion. But just here, what I would like to recall is that to get the usual veil law, the veil law comes from what is called the local veil law, which is estimates on the heat kernel. And by the way, what is called microlocal veil law is when you integrate the heat kernel not along the diagonal and against a pseudo-differential operator. Because here you integrate against the operator, which is the multiplication by f. But if you replace f by op of a, and that you integrate also outside of the diagonal, you obtain what is called the microlocal veil law, which is much more general. Okay. Anyway. So this gives you the value of this maximum, right? Well, for the moment, it's far from being satisfactory, but this is what we have. Now we would like to have also existence, right? We will have to have existence of an optimal set. And already in 1D, the situation is very difficult because, well, in 1D, it can completely be solved. Actually, my claim, so this is by Fourier series, quite simply, but the relaxed problem has an infinite number of maximizers that are all given by such Fourier series. So this is a usual Fourier series, right? With the constant coefficient, which is equal to capital L, and then you have a linear combination of cosine and sine, as usual in a Fourier series. But these are Fourier series with coefficients aj that are non-positive, which is strange. This is a strange set of Fourier series that have been a bit studied, but not much, by people in harmonic analysis, because it's not at all usual to put some constraints on the Fourier coefficients. You are not used to that, right? Me too. Okay, it's not usual. But this is what we obtain. So this is why already in 1D, the situation is quite difficult. Now, let me come to the complete statement that we have been able to derive, and that unfortunately is still very partial. So we have proved that under assumptions that I'm going to comment, the initial problem, that is the problem of maximizing over subsets, is indeed equal to the maximum over the convexified problem. That is, it's a result of no gap. We have no gap between the initial problem and the relaxed problem under some strong assumptions. So the claim here is that this supremum, the value of this supremum, is equal to capital L. And I will now comment on the assumptions. First, mainly we have to deal with high frequencies. And if you expect such a result to be true, well, it could be nice that at the limit for high frequencies, when J tends to the infinity, this guy, this mu j of omega, be almost equal to capital L, because it's a way. And so when is it true? Well, so quite evidently, this fact is true if you assume that all measures, all probability measures, mu j equal to phi j squared dx, converge weakly to the uniform measure. In that case, it is true. Right? So if all probability measures phi j squared converge to the uniform measure, that is, high frequencies equidistribute, oscillations everywhere, so you have equidistribution at the limit, then you are done. Then you are done. So what happens? This is the main assumption, right? Is this assumption reasonable? Let us first look at the 1D situation. In 1D, yeah, fortunately it's true. It's true because in 1D, for the Dirichlet-Laplace the eigenfunctions are given by sine of Jx. But of course, I already told that yesterday or the day before, sine square of Jx converges weakly to 1/2. And so the property is true. I mean, in 1D, if you take high frequencies, these are sine square, that oscillate in a very regular way, and whose number of oscillations is increasing with J, but you see at the limit, in average, you obtain the uniform 1/2. So it's okay. In 1D, this big assumption here is satisfied. Now, now in multi-D. In multi-D, it is far from being the case, unfortunately. Already in the square, or maybe I have some slide further, I think. Yeah, I have a slide here. Yeah. So in 1D, okay. This is the case. In 2D, let us take the situation of the square. And by the way, I forgot the square here. Capital omega is 0p to the square, okay, the 2D square. What are the eigenfunctions? Well, you well know that the eigenfunctions are products of sine functions, right? So, what are the quantum limits in that case? What are the possible weak limits of the eigenfunctions to the square? It means that you have to take, so phi j k square is what? It is sine square of jx times sine square of kx. What are the limits? Here, at least, we are able to compute all of them, right? Because this converges to, so the whole converges when j and k tend to the infinity, converges to 1/2 times 1/2, so 1/4. That's good, the uniform measure. Yeah, but it is not the only limit, right? Because I made 10 to the infinity the two indices. But if instead of that, I let, for instance, j fixed and k tend to the infinity, then in that case, it does not converge to the uniform measure. Of course, because you keep the sine square as it is. It converges to 1/2 of sine square for any j. So already, and symmetrically with k, right? So actually here you see that you don't have a unique quantum limit. You have an infinite number of them. patatras. How you say patatras in Hindi? Badaboom. No, you don't have a unique limit. You have plenty of them. So already in the square, the previous assumption I did in the theorem is wrong. It's not satisfied, unfortunately. Now in the disk, let us look at the disk, because also in the disk, we are able to parameterize all eigenfunctions, right? Thanks to Bessel functions. And in that case, we are also able to compute all quantum limits. It's a bit more difficult, right? But it can be done. And so I will not give you the set of all quantum limits, except one which is interesting, and that you all already know for sure. I claim that among the quantum limit of the 2D disk, that is among the weak limits of the phi j square, dx, there is one particular measure that is interesting, which is the Dirac along the boundary. What does it mean? It means that there exists a subsequence of integers such that the corresponding phi j square do converge weakly to the Dirac at the boundary. That is, you have something like that, you see. These are the sequence of high frequency eigenfunctions to the square. I mean, there is a subsequence of phi j square such that, well, in the middle of the disk, you have very, very small oscillations, but essentially the function is flat, okay, essentially. But at the boundary, it's becoming very large while oscillating. So the phi j square dx converge to the Dirac along the boundary. This is one of the quantum limits. And this quantum limit is actually well known because it is the quantum limit that exactly explains the phenomenon of whispering galleries that you all know for sure, right? No? No. So it was described, probably not discovered, but it was described by Lord Rayleigh, 150 years ago, something like that. He was in a church in England with a dome, right? And in this dome, he observed that, so let us assume that you are in a room, let's say that is a cylinder, right? You are in a room that is a cylinder, it's the same. Now, you put someone here, a talker, and you put another guy here who will listen what happens. And imagine that the room is very large. Okay, the radius of the cylinder is very big, very large. Now, if the guy is talking, not comment on dit chuchoter, talking very low, whispering, whispering, absolutely. So the guy is whispering. Imagine that the guy is whispering in the normal direction. Then the guy in front won't hear anything. But now, imagine that the guy is whispering tangentially. So then the signal is propagating, assuming that in the whisper there are some high frequencies. Otherwise, it does not work. The signal is propagating, it's very intuitive, and coming to the guy in front of. This is the well-known phenomenon of whispering galleries, and in some church in London, I do not remember the name of the church, but the church shown by Lord Rayleigh, there is a dome like that, and if you are at some place in the church, you whisper, and someone who is very far away can hear you. It's well known. And it is explained, this phenomenon, which is quite funny, is exactly explained or reflected, I would say, by the fact that the Dirac along the boundary is a quantum limit. It's exactly that. Now, these simple examples show that there is a basic question that we should investigate in order to try to approach our problem. And this question is very much difficult. It is the question of knowing what are the possible limits of all probability measures, mu j equal to phi j squared dx. I mean, what are the possible quantum limits? What are the possible semi-classical measures? It's essentially and very widely an open problem. An open problem that is making very busy many mathematicians in the whole world, the world of semi-classical analysis. Each one would like to determine new quantum limits, and only very few are known. I showed you very simple ones in 1D, of course, in 2D, for the square, for the disk, and, well, essentially, that's all. Almost. Actually, what is known, it is there that you have to enter into dynamics, complex dynamics. If you look at the geodesics that are propagating inside capital omega, well, there are many differences between integrable dynamics, like it is the case for the disk, for the square, for ellipses, and chaotic systems. That is when your billiard, because you play billiard, we say that a dynamical system is chaotic whenever you take almost every geodesic, fills up almost all the space in infinite time. This is chaos. So of course you don't have chaos in the disk, because if you play billiard in the disk, you will have a trajectory which at most may fill up a ring like that. And this is why, by the way, quantum limits are necessarily supported on such rings, necessarily. While, what would you say, what would you guess here for chaotic systems? What would be your guess? What can be a quantum limit of such a system, according to you? I don't want any attractor. Really take the most chaotic situation, right? So you take geodesics that fill up, almost every geodesic fills up almost the whole space. Oui, yes. This is what we would expect, right? We would expect that the whole sequence of phi j squared dx converges to the uniform probability measure. Equidistribution of energies, right? This is perfectly intuitive. Well, this question is not answered. Not answered, and where is my slide? Oh, it's probably here. No, it's not here. It's here, yes. There is a famous conjecture formulated a long time ago already, you see, 1994, by Rudnick and Sarnak, that is called the QUE conjecture, quantum unique ergodicity conjecture, that postulates that the property, Vannet, that you describe, that is, there is a unique quantum limit that is the uniform measure. So this property is called QUE. They postulate that QUE is true, not every time, for every compact manifold having negative curvature. This is what is felt. And people now, since the 90s, are searching for counter examples to quantum chaos, to QUE. In particular, they are working very much on capital omega, which is a stadium. So what is a stadium? It is a rectangle with two half disks, okay, a stadium. like a pill, you know, but a 2D pill. Mais ça va mieux. Why do they think? So people think that in a stadium, QUE fails. And this is because of numerical experiments, because what they do observe on numerical experiments is what these people call bouncing balls. That is a kind of accumulation of energy exactly here at the boundary between the rectangle and the disks. But nobody is able to explain these numerical simulations. In any case, when QUE fails, we may have what people, mathematicians and physicists, call scars. Scars, les cicatrices. Traces. Scars, sorry. So scars are energy concentration phenomena. I mean, you may have subsequences of eigenfunctions that do converge to something, a Dirac along something. And this is the existence of scars has been shown experimentally on chaotic situations, but still not proved. And I can tell you that many, many people on Earth, including Nicolas Burck, are working on that. Many. Anyway, at least there is one result that is almost what you said, Danny. That is almost QUE, which is very famous. This result was stated by Schnirelmann in the great year 74. Great year for me. You will guess why. But Schnirelmann stated this result without proof, actually. The result says, so let's go back a bit to geometry. The result says that if you are on a compact Riemannian manifold with a metric G, look at now the geodesic flow, look at all geodesics, and assume that the geodesic flow is ergodic, that is chaotic, right? Almost every geodesic fills up almost all the space. This is ergodicity. Then the Laplace-Beltrami operator enjoys the so-called quantum ergodicity property, meaning that, I think it was on my slide before, I'm sorry. Yes. Meaning that, in some sense, almost all subsequences converge to the uniform measure. Almost all. In the sense, to be precise mathematically, in the sense that the subsequences that converge to the uniform measure have density 1. Density 1 means, you truncate at capital N and you count the number of indices that will work, that will finally converge to this uniform measure. You count them. Then you divide by capital N because you make the average. And it converges, this mass converges to 1. So this is density 1. So it means, according to this beautiful theorem due to Schnirelmann, it means that if there are some subsequences that converge to something else, like a Dirac, the sequences are very exceptional. They have density 0. So it means that maybe if you look at the sequence of eigenfunctions to the square, only from time to time you pick up an index, and according to this very exceptional sequence, you will have a convergence to something else than the uniform measure. This is terrible, right? And this is completely counterintuitive. This is why this is so much difficult. Where am I? Yeah, and people in quantum physics in particular are very, very much interested in estimating quantum limits. Why? Because in particular for optic fibers, for instance, when you want to propagate signals in a small wire, you really have an interest that inside the wire, since you are dealing with high frequencies in a fiber optics, you have an interest so that you don't have any concentration phenomena, right? Right, but look, unfortunately, in the disk, you systematically have a concentration at the boundary, which is the Dirac. So it means that when you build an optic fiber, building up a cylinder is the worst possible choice. That's crazy, right? It's the worst possible choice. I mean, if inside a cylinder you send very high frequencies, too high frequencies, what will do the wire? Psh, it will burn. So it was the worst possible choice. but it's like that. I mean, how to, in practice, maybe if the stadium-shaped enjoys QUE, how to build such a stadium-shaped wire. You see the engineering problem that are behind. And in France, for instance, CEA, le Commissariat à l'énergie atomique, is working very, very much on that. Also for other reasons of blow-up, as you can easily guess. Okay, so this is the relationship, but I have to conclude now. So let me switch all of that, and let me switch all of that, and let me just give, to finish, very quickly, let me give some numerical approximation for waves, because we saw now that for waves the situation is very unclear. However, for waves, we can also solve the truncated problem, right? And give the shape of the solutions omega n. But unfortunately, and as you guessed, because of these high frequencies, if now you let capital N tend to the infinity, you will see the complexity of the set omega n that is increasing, unfortunately. So look, this is in the square. This is for different values of capital L, okay, by rho. And you see that if each time you increase the number of modes, in some sense, the subset is getting to something quite fractal. Well, it's like that. And it's probably due to, it's undoubtedly due to high frequencies that tend to equidistribute. That's great, but not all of them. How to deal with that? I do not know. I do not know. We have the same kind of phenomenon in the disk with accumulation of concentric rings at the boundary, which is exactly the same phenomenon as for anomalous diffusion equations, interestingly, which means that in some sense, for alpha less than 1/2, anomalous diffusions are quite of hyperbolic, right? And even, maybe one word about that, even we have been able to prove a very bad theorem in 1D, because in 1D we have proved, so this is the contents of this theorem, but let me rather comment the consequence. We have proved that in 1D, the optimal domains omega n enjoy the very nasty spillover phenomenon. That is, look, the nightmare. If you take the best domain omega n for the n first modes, then this guy is the worst possible domain when now you take n+1 modes. So you see the instability. The instability is the worst possible. It's a nightmare. And it's really due to the wild oscillation of waves, as you can imagine. This is why, well, we think that in some sense there is no hope to solve to solve this problem. Actually, see, here is a rapid comparison between the world of wave or Schrödinger equations, for which essentially we have negative results, say, and the world of, and the parabolic world, in which at the very, very contrary, we have a definitive and beautiful result with uniqueness and all you want. This is dramatically different. And also, by the way, for the existence of optimal solutions, of optimal sets, I did not comment about that, but in 1D, we are able to solve the problem of the existence of an optimal set for some values of capital L, which I don't have time to explain, but just let me tell you that this is related to arithmetic considerations. And there is a kind of resonance phenomena already in 1D. So it became so much complicated, and I'm not acquainted enough with arithmetic and number theory that at the end we stopped because it was becoming unreasonable. But anyway, I can draw a rapid conclusion, which is unsatisfactory, I know, but this is what we have at the moment. In this study, finally, we have shown a close relationship between shape optimization and quantum chaos. And maybe, yeah, this is the novelty in some sense. Even if we have some negative results at the end, this is the main novelty. A close relationship between shape optimization and quantum chaos, which is in some sense, well, which is expected if you think about it, but which was a surprise several years ago. And finally, if we get some knowledge of on the quantum limits, if we know that the supports of the quantum limits are there, then of course you will have a strong interest in placing sensors exactly there. Of course. Imagine that you have at least one quantum limit which is supported, say, here. Okay? This is the support. This is this bottle. And now, if you put sensors here with no intersections, then you cannot have any observability. Of course, because here you have a sequence of modes that concentrates here. So you cannot observe them. You see? So there is an obvious necessary condition, which is my set of sensors must intersect, at best, the supports of quantum limits. So this is the only conclusion I can give, because at this day, currently, we do not have any more knowledge on QLs, on quantum limits. This is an open problem. So let us stop there. Let us stop. And also another result that was very fundamental for treating the parabolic case was this kind of very beautiful exponential concentration properties obtained by Aprez, Escoriaza, Wang, and Zhang. Up to my knowledge, this is, until now, the only paper, except one more on Stokes, in which there is such results on concentration properties. So here there is much stuff to be done, much stuff. And it is of great interest, as I said, to those people dealing with quantum physics. So many open problems there, many. But it's difficult. This kind of result is difficult because it has to be uniform with respect to all measurable subsets. So it's a difficult open problem. And finally, let me give you maybe 2 or 3 other open problems. So, as I showed yesterday, and at least it is proved for the limit in time, you remember, the observability constant for the wave is essentially the minimum of 2 quantities. At least it's a conjecture for finite time. Okay. The first quantity is purely spectral, and as I showed, this spectral quantity, which I called also G of omega, is also the randomized observability constant, right? And this is the constant that we have tried to maximize today. So in maximizing this quantity, it means that we have maximized half of the truth, in some sense, right? And the other quantity that is in the minimum is purely geometric. It is the LT of omega, which is measuring GCC. So here there is an interesting, to my opinion, there is an interesting shape optimization problem that would consist of optimizing this functional. It has never been done. I think it's interesting. It's a problem which combines shape optimization with geometry and geometric considerations on the geodesic flow. Interesting. So there is an open problem, and I would like to be able to maximize also this quantity and compare, see, in a hope that this would finally lead something for the true deterministic observability constant. And another completely open problem, very, very open, I never touched it too, is on discretization issues. As you saw in the lectures by Jean-Pierre Raymond, dealing with discretization issues and trying to prove convergence results is really difficult. It's an issue. So here, how we can do? The basic questions, the basic naive questions, I would say, is, okay, you truncate the problem and do the numerical optimal designs that you get with, I don't know, with finite elements, for instance. Not the way I described before. You make some numerical analysis, finite elements, for instance. You compute the optimal designs on it. Do they converge to the continuous optimal set as the mesh size would converge to 0? We have left untouched this very important question, but as you can imagine, this question is the main one in engineering. Really the main one, this for sure. So you will find on the internet many papers in Automatica, in engineering, dealing with this question. But the main problem in all these papers is that never the authors do care about whether or not there exists a limit. So I'm laughing a bit, of course. And, and if the article is for wave equations, I know in advance that there is a problem, right? Because there is no limit. So there is a true question that is also of particular interest in engineering. And so I'm sorry for the few minutes late. I will definitely stop here.
So thank you, Emmanuel, for the wonderful talk.
Okay, thank you. Yes, I have a question concerning the wave equation. So your theorem, when your theorem could be really applied. So on the one-dimensional case, it's okay, as you said. But do you have other example in multidimensional case where you can apply your positive result or not?
So for wave equations, unfortunately, no, I have no positive result in multi-D in general, except,
okay.
Except in 1D, I said, yes. In the square too, but in the square we have since the square is 2 times 1D tensorized, okay. You have exactly the same phenomenon of resonance, yes. With arithmetic considerations. So okay. I know how to prove that there exists an optimal set in the square for particular values of capital L only. Okay. Capital L equal 1/4, okay. I don't remember. Okay. Particular values. Okay. But for all other values, I know also that there does not exist an optimal set. So it's okay. Bound to fail.
Okay. But in your theorem, you need to assume that that let's say the quantum limit was the uniform one,
Yes.
but it does not contradict your example that you have given here for the square? No?
You are right.
No?
In the case of the square,
Yes.
so we have no QUE, the theorem does not apply, but
okay.
I can do explicit computations.
Okay, understand. Okay.
Sorry, maybe I forgot to say, no, I'm sorry. But for the square or the disk, or the wave,
Yes.
neither the square nor the disk do satisfy QUE, far from that.
Yes.
But anyway, I can solve the problem by another way, explicit computations.
Okay, and on the torus, do you have some kind of information of the quantum limits, or is it known, or?
No, in the torus, it's exactly the same.
Okay.
It's the same eigenfunction, you just have cosine.
Yes,
so,
right. Okay.
No, unfortunately.
Okay, thank you. And I have another question concerning the parabolic case. So, can you just explain again where do you use the analyticity of the operator? Yes,
I don't remember.
Yes, because perhaps it's technical, but just to understand.
I don't remember.
Yeah. Because you have given a proof, I believe. And...
Oui, tu as raison, mais...
Yes.
No, we don't use the fact that you mean the semi-group is analytic?
No. The A, so A, okay, so my question, I can just reformulate. Can you replace the Laplacian by, for instance, another elliptic operator like Laplacian plus a potential, and the potential is not analytic, for instance?
Yes.
Okay.
No.
Yes, yeah, no, you cannot.
Not an analytic potential, yes.
Yes, okay.
A smooth potential, I do not know.
Okay.
Because, I don't need analyticity of the semi-group, right?
But
what I need is, so this assumption I did not comment, I'm sorry. But the basic assumption I need is that the operator be analytic hypoelliptic. So what does it mean? It means that when you solve AF equal G with G which is analytic, then F should be analytic.
Okay.
This is hypoellipticity. Okay. Hypoellipticity is with C infinite.
Yes.
But here I require hypoellipticity with analyticity.
Okay.
Property which is called analytic hypoellipticity, which is true, obviously true for an elliptic second order operator with analytic coefficient.
Okay.
Because thanks to that property, actually, all I need is that the eigenfunctions themselves be analytic. Okay. This was for the bathtub principle.
Okay.
If you don't have the analyticity of the function in the bathtub principle, you may have relaxation. That's all. That's all.
Okay, perfect. Thank you very much. I understand.
This, you mentioned the concentration on the boundary. Such quantum limits are extreme points.
Okay. So first, a very interesting question. So what is the structure of quantum limits? So first thing, quantum limits must be, it's a consequence of the Egorov theorem. Quantum limits must be invariant under the geodesic flow. So if you look at the set of quantum limits, it's itself a subset of the set of all probability measures that are invariant under the geodesic flow. Okay? It's a fact. It follows from Egorov. Actually, it's perfectly intuitive because if you think of the geodesic flow, and if you have geodesics, let's say at some point concentrating, let's say along a periodic orbit, so that this periodic orbit gives you a quantum limit, it is the Dirac along the periodic orbit, you immediately understand that this probability measure has to be invariant under the geodesic flow. You see, it's just a matter of propagation. So Egorov theorem gives you that. Now, it is postulated, not proved, that quantum limits are the extremal points of the set of invariant measures. It is postulated. It would be already a nice thing to know that, but it is not even proved. It is felt by experts. It is not proved, but it would already be a great fact. And last remark, we could wonder whenever there is an equality between quantum limits and invariant measures, or if the set of quantum limits is a proper subset of the set of invariant measures, right? We could wonder that. So the fact is that on a Zoll manifold, a Zoll manifold is a manifold on which all geodesics are periodic. So the sphere. The sphere is a prototype for a Zoll manifold. On a Zoll manifold, it has been proved by Steven Zeldich that the set of quantum limits coincides with the set of invariant limits. It means that every invariant measure is a quantum limit. In particular, on the sphere, you take any geodesic, which is a circle, right? An equator, for instance, then this equator must be a quantum limit, which is perfectly intuitive. It was, the proof by Lebeau. You can design Gaussian beams which concentrate along this grid circle. But the fact is more general. It's true on every Zoll manifold. And it has been also, it's interesting. There is an inverse problem here. I have tried to work on it, but I failed. There is an interesting inverse problem. If you assume that the set of quantum limits is equal to the set of invariant measures, then the manifold has to be Zoll. I was not able to prove, but I feel it's true.
So I have just one question, that in the parabolic case, what you have shown, by that one, can we get something for the parabolic income inequality, some constant on that?
No. No, because in what I show here, you really deal with single modes.
Single mode.
You have no interactions between modes. While in INGAM, of course, the main game consists of killing the interactions, right? But here I do not deal at all with interactions between modes.
And that means that in the hyperbolic case also, the constant corresponding to those incomes, and this constant what you are recovering, there is only one side.
There is no link. No,
okay.
No, really not. And well, it's not a complete claim, but it's rather my feeling. When writing the observability constant as a minimum of two quantities, so the first quantity is the randomized observability constant, and it is for a quantity for single modes, standing for spectral observability only. So there is no INGAM there. And the second quantity is purely geometric, dealing with the GCC functional state. And it is inside this functional that you can see the interactions between modes.
So if there is no other question, let us thank Emmanuel again. And